Hey guys, Greaves here. Let's take a look at review number 15. Got to say about review number 15, just like I said about review 14, here's a perfect example at what I think could be asked on this year's AP. Why is that? No calculations, no calculator, just flat out, hey, you guys know what's going on. Okay? So let's take a look. Have a spacecraft, right, of mass m circling Earth, radius r. Okay? Mass of the Earth is me. Right? So in the figure below, draw and label the forces, not components, right? Acting on the spacecraft, right? So what is the force that's acting on this? Well, first of all, it's traveling in a circle, right? So if it's traveling in a circle, I have to have some force, right? We call it the centripetal force, right? Which is enabling the object to travel in a circle. And remember, the centripetal force, right, is always, right, pointed towards the center. So Fg, right? So there is the only force acting on the object as it travels in a circle, right? Fg. Okay. Now, derive an equation for the orbital period of the spacecraft in terms of m, mass of the spacecraft, me, mass of the Earth, r, distance, and physical constants, etc., right? So let's see if we could take a look at that, okay? So what do we got here? All right, so we're going to use Newton's second law, obviously. F net is equal to ma. What's the only force acting on it? Gravity, and we can rewrite that as G, me, m of the spacecraft, r squared, is equal to m of the spacecraft. Don't forget A is equal to v squared over r. So we can do some slash and burn. Mass of the spacecraft goes away. Mass of the spacecraft goes away. 1r goes away, and 1r goes away. Okay, so that reduces to G, me, r is equal to v squared. All right, well, let's take a look at the velocity of this object, right? Velocity is always distance over time. In this particular case, since we're traveling in a circle, the distance around the circle is 2 pi r, and we call that the period, right? Time is the period. So we're going to take this, plug it into here, right? So I have G, me, r is equal to, let's also do a little bit of squaring, right? So 2 squared is 4, pi squared, r squared, t squared. Right, now we can simplify a little bit, right? So we're going to get the t to this side and bring everything over here. So r comes up here, gm comes down here, and t goes over. So t squared, 4 pi squared r cubed. R squared, r cubed, right, over what? Gme. Now you can leave it like that, or you can take the square root, so t is going to be equal to 4 pi squared r cubed Gme. So there is going to be our expression for the orbital period, okay? So let's take a look at the next one, right? So what do we got? The second spacecraft, doubling the mass, is placed in circular orbit. Doubling the mass. Right? So is the orbital period what happens to this orbital period? All right, so if I double 2 times m of the spacecraft, what happens to the period? Well, the answer is nothing happens to the period. Why is that? Because the period, right, is not dependent upon the mass of the spacecraft, it's dependent upon the mass of the Earth. So the answer here is equal. And my explanation, right? A period not dependent upon the mass of the spacecraft. All right, so next one. All right, so now I'm taking the first spacecraft. So we're moving the spacecraft farther away, right? Farther away. So what happens to the speed now? All right, so what happens to the speed? All right, so looking at this equation, there's a couple of ways that I could look at it. Look, if I make this bigger, obviously the period is going to get bigger. So if the only way the period gets bigger, the time needed to go around once, is if the speed slows down. Another way to look at it is up here. Look, v squared is equal to, right, this equation here. So making this bigger, doubling the denominator, right, or increasing the denominator, right, makes that smaller. So what happens to the speed? Speed is less. Why is that? Because looking at either this equation, right, or this equation, right, that tells me. Okay, so that is 15.